To derive the equations of modern physics, from orbital mechanics to electromagnetism, physicists rely on a single mathematical tool, the principle of stationary action. This principle assumes that physical systems evolve along paths that minimize a specific mathematical quantity. In standard quantum field theory, we calculate this action over a uniform, unchanging measure of spacetime. By freezing that background measure, we force the mathematical model to assume the stability of matter right from the start, rather than allowing that stability to generate itself dynamically. If we want to understand how coherent structures, what we observe as physical particles, actually form and hold together, adding more hypothetical particles to the equations doesn't solve the underlying problem. To describe a universe that builds its own structural order, we have to rewrite the bedrock variational principle itself. This brings us to the AE framework. Its central thesis is straightforward. The integration measure of the action cannot be a static grid. It must be dynamically weighted by the system's own phase coherence. In practical terms, we are encoding a structural bias directly into the math. The equations themselves will penalize chaotic configurations and reward structural order. This 3D surface plot represents the coupling energy field. The yellow and purple gradient shows the energy coupling intensity, a landscape of coherence dictating how much energy is required for structures to interact. Next, we construct this model from first principles. We will demonstrate how coherent structures manage to persist as observable phenomena without relying on any undiscovered physics. Before we can calculate any dynamics, we have to define the mathematical space where these physics happen. We use a weighted functional space called L2A. The first primitive functional required in this space is phase entropy. In this context, phase entropy does not refer to physical heat or thermodynamic dispersion. It strictly measures the mathematical variance of phase alignment across the field. This naturally introduces its inverse counterpart, the canonical coherence functional, denoted as C. The relationship is tightly constrained. As the field's phase entropy drops towards 0, its coherence mathematically approaches 1. At this stage, these variables do not describe physical matter. They define the raw capacity for the field to maintain an organized state. We combine phase entropy and canonical coherence to create the architectural linchpin of the theory, the weight function. This weight function acts as an active filter on the Hilbert space. It mathematically suppresses highly entropic, chaotic field configurations, preventing them from dominating the system. Using this filter, we construct the new master action integral. When we place this next to the standard quantum field theory action, the difference is immediate. The standard model lacks this dynamic weighting term entirely. By inserting the weight function, the local physics, the Lagrangian, is permanently and inextricably linked to the global phase entropy of the entire system. Changing the bedrock integration measure forces the mathematical universe to evaluate its own structural order before it takes a single step forward in time. To see how this system actually moves, we apply the Euler-Lagrange variational principle to our new master action. Taking the variations of these weighted fields yields a new set of gradient terms that simply do not exist in standard physics. From these new equations, we extract the specific operator that governs fermions, like electrons. We call this the Dirac meta-operator. Unlike the standard Dirac operator, which uses a hard-coded mass term, the Dirac A operator injects topological and entropy-dependent corrections directly into the particle's behavior. To understand the geometric properties of this operator, we square it. Squaring the Dirac-Au operator yields an effective Klein-Gordon emergence. What we typically measure as a constant particle mass suddenly appears as a dynamically generated scale. Mass is not an intrinsic building block of the universe. It is an emergent property, created entirely by the field's local phase organization. We have the action principle. Now we have to calculate how this system actually flows through time. Standard Hamiltonian mechanics relies on symplectic geometry, which is designed to handle binary pairs of variables, like position and momentum. Here, that breaks down entirely. We must upgrade to Nanbu mechanics, a mathematical framework that allows for multi-observable dynamics. This is a mandatory step. To determine its next state, the system has to process its phase, its coherence, and its local fields simultaneously. To model a self-organizing universe, the mathematical framework has to upgrade its own internal geometry to handle complex, interdependent relationships. We track the stability of the Dirac A operator across different physical sizes using a mathematical tool called the resolvent. By mapping the renormalization group flow, we can trace how these coherent structures reorganize themselves, moving from microscopic quantum scales all the way up to macroscopic cosmological scales. To prove the validity of the A model, we subject it to a mathematical stress test. We force the phase entropy variable to exactly 0. This triggers a mathematical cascade. As entropy vanishes, the coherence functional maximizes, and the weight function normalizes to exactly 1. Once the weight function normalizes, the complex A master action collapses perfectly into the standard equations of gauge field theory and Einstein relativity. Standard modern physics is entirely correct within its domain. It is simply the special zero-entropy limiting case of the broader A framework. By modifying a single bedrock integration measure, we successfully generated mass and time evolution dynamically, without having to invent any hypothetical particles. However, this model contains a significant unresolved mathematical vulnerability hidden inside the master action. This specific integral acts as a memory kernel. It forces the current state of the field to account for its own historical phase entropy. In functional analysis, operators with non-local, non-linear historical feedback loops are notoriously difficult to prove stable. They frequently diverge into mathematical infinities. The theory remains perfectly elegant locally, but proving that this historical memory loop doesn't mathematically break the universe remains an open topological challenge. This leaves us with a high-stakes mathematical question. What happens if someone successfully solves this global well-posedness problem? Proving that the Dirac A operator remains bounded under non-local memory evolution would demonstrate that this historical feedback is a stable mechanism for the preservation of information in a dynamical field. It would provide rigorous proof that long-range memory and coherence can stably self-organize within a quantum field, forming the persistent topological structures the framework calls reality knots. By providing a formal link between topological stability and informational organization, this math offers a tool to describe systems as complex as DNA, which the framework defines as a long-range phase memory structure. The equations of the A framework describe a universe where the past state of the field is an active, stabilizing ingredient in the present, the mathematical architecture of a reality that remembers itself.